Hello everyone. On this video, we will be looking at the derivatives and integrals of vector valued functions. Okay, and just like before, the derivative is just really close to the derivative for a real valued function. Not a whole lot change. Some of the properties are a little different, but for the overall part, the derivative and integral portions of it are pretty much like your real valued functions. Okay, so the derivative of well, not derivative, it's more the limit. I'll do the derivative next. So I'll say the limit definition of a derivative. Of a derivative for a vector valued function. That's probably a little for a vector valued function is defined by, okay, so you have your r vector of t, just r prime, just like before, is equal to the limit of r vector of t plus delta t minus r vector of t all over delta t is delta t approaches 0. Or it could be h approaches 0 or some other variable there. We're just using delta t. Okay, and that's for any t where the limit exists. Okay, so with that definition 1, if you have some r vector prime of c that exists, then it's differentiable at that c. And my differentiable, instead of writing it all out, that's my differentiable shortcut at whatever that value c happens to be. And also, if it does exist, our vector prime of c exists, of course, for all c, in an open interval, and that interval we'll call I. Then it's differentiable over the entire interval. The entire interval. Okay, which leads us to our derivative formula, like I said, which is almost identical to the formula you've been using all along for real valued functions. All right. If, let's say we have r of t is equal to f of t times the I vector plus g of t times the j vector. Remember, that's in 2 dimensions. Or r of t is equal to f of t times the I vector plus g of t times the j vector plus h of t times the k vector, which of course is in 3 dimensions. Okay, and we know that each one of those component functions are differentiable at whatever value of t. So we know that's where f, g, and h are all differentiable. Functions at t. Okay. Then we know that r prime of t is equal to the derivative of the first component function plus the derivative of the second component function in 2 dimensions, or r prime of t is equal to the derivative of the first component function plus the derivative of the second component function plus the derivative of the third component function. And that's in 3 dimensions. All right. So like I said, the definition did not change a whole lot. Okay. So if you are writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay, so if you wanted to look at the derivative visually, all right, so if we have our x, y, and z, let me move that out a little bit more so it's clearer. There we go. Okay, so let's say if we have our first vector. Okay, so let's say that's r of t. Let's say if we have our second vector, and that's vector r of t plus delta t. Okay, so we have our vector here, and this vector is actually, let me move this up a little bit more, r of t plus delta t minus r of t. That's this vector here. Okay, so let's say if we have a curve that goes across those 2 terminal points. Okay, so you have your r of t, r of delta t. Okay, so as delta t, which is the distance between these two, gets shorter and shorter and shorter, it gets closer and closer and closer. Let me move this r of t out of the way. R of t down here to the slope at r of t. So that's your r prime of t. All right, so just another quick note that r prime of t, you may also see that as the derivative with respect to t of rt, or you may also see it as the derivative with respect to t, which is just a uppercase d with a subscript of a lowercase t of rt, or you may even see it as the derivative of the r vector with respect to t. All of those mean the exact same thing. All right, so let's go ahead and jump to our first example. Okay, so what if we wanted to find r prime t for r of t equals 6t times the I vector minus 7t squared times the j vector plus t cubed times the k vector. All right, so most of this should look very familiar. You've probably been doing it all along, but just a quick review. Okay, so r vector prime of t is going to equal the derivative of 6t, which is just 6. So you have 6 times the I vector minus the derivative of 7t squared, which is minus 14t times your j vector, plus the derivative of t to the third, which is plus 3t squared times your k vector. So again, that one was pretty straightforward. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next example. Okay, so let's say, for example, we know 4 r of t equals t to the third times the I vector plus 1/2 t squared times your j vector. We want to find, let's say for problem A, we want to find the second derivative of r. And let's say for problem B, we want to find the dot product of the first derivative and the second derivative. Okay, so derivatives are the same from Calc 1, but we're kind of throwing in some of our Calc 3 with that dot product. Okay, now quick note. You can also write your r vector of t as just the components of your, well, just your function component. So that's t to the third 1/2 t squared. So you can also write it that way if you're not comfortable doing the dot product in this form. You can also write it like that. All right. So for problem A, we know we have our r of t equals t to the third times the I vector plus 1/2 t squared times j vector. Now, derivative of that, okay, so you have the derivative of t to the third, which is 3t squared times your I vector plus 1/2 t squared. 2 comes down, they cancel out, so you just have t times j vector. Okay. Now your second derivative, just the derivative of the first. Derivative of 3t squared is 6t times your I vector plus derivative of t is just 1, so you have 1 times j, which is just your j vector. Okay, so you have your second derivative. Okay, now if you wanted to, you could write it as (6t)(1). If you wanted to write it in vector form. Okay, so for question B, you want to know the dot product of the first derivative and the second derivative. All right. So if we get our first derivative, remember that our r is t to the third 1/2 t squared. Our first derivative, we can actually rewrite that as 3t squared and t. Okay, so our first derivative of t is 3t squared t, and our second derivative is 6t1. Okay, now remember with your dot product, you multiply the first terms. So you have 3t squared times 6t plus, now you multiply your second term, t times 1. Okay, so you have 18t to the third plus t. So that's the dot product of your first and second derivatives. All right. So if you are still writing, feel free to press pause. But now we're going to go ahead and move on to our next page, which will cover the properties of derivatives. Okay, now some of these are very close to real valued functions, but when you get to the dot products and cross products, that's when you have to pay attention. You don't want to make the mistake of thinking the dot product and cross product will have the same properties as the real valued derivatives. Okay, so what if we let a vector and b vector represent differentiable vector values? Represent differentiable vector valued functions. Okay. Now some of those may have a scalar value of c, and our function f, or f of t, is a real valued function of t. All right. So we're going to go ahead and go to our first property, which is pretty close to the regular definition of the derivative that we're used to. So if you have the derivative with respect to t of a vector of t, and this works for either plus or minus, b vector of t, that's of course a prime of t plus or minus b prime of t. Okay, so just like the real value derivatives. Okay, so for number 2, you have the derivative with respect to t of a constant times a vector of t. Just like with the real value, you have that constant times the derivative. Okay, so going on to the third one, you have the derivative with respect to t of a real valued function times a vector valued function. Okay, no dot product, just straight multiplication. Okay, that's equal to the first times derivative of the second plus the second times derivative of the first. Or the a of t, not the derivative. Which is why I don't know why I put that there. Alright, don't know why I put that derivative there when it should have been there. But this is your formula for that one. Alright, so fourth, let's say you have derivative with respect to t of the dot product of a and t and b of t. Okay, now this is a little bit different because it doesn't cover the product rule for derivatives. Okay, so you have a of t and the dot product of b prime of t plus derivative of a and the dot product of b of t. Okay, and this one's proven in your textbooks. Okay, so for number 5, you have the derivative of the cross product of a and b. Okay, so that's going to equal the cross product of a and b prime plus the cross product of a prime and b. All right, so for number 6, we have the derivative of the vector a, but instead of having a parameter of t, you have a parameter of f of t. Okay, so that's going to equal a prime of that f of t times f prime of t, which is just basically the chain rule. All right, and last but not least, we know that if the dot product of a and itself is equal to constant, okay? Or another way you can write it, in other words, the magnitude is equal to c. Then we know that the dot product of a and the derivative is equal to 0. Okay. Or in other words, it's saying that the a vector is orthogonal to its derivative. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and jump into our first example of our properties. All right, so let's say, for example, let's say for a of t equals 1 over t times the I vector minus your j vector plus natural log of t times your k vector And let's say your b of t is equal to t squared times your I vector minus 2t times your j vector plus your k vector. What if we wanted to find the derivative of the dot product of your a and b vector? All right. So first thing we have to do is find a prime and b prime because we're going to need it at some point. So a prime of t is equal to derivative of 1 over t is negative 1 over t squared, and that's times your I vector, plus derivative of negative 1 is 0, so that j just disappears, plus derivative of natural log of t is 1 over t, times your k vector. Okay, and we know that b prime of t, derivative of t squared is 2t, times your I vector. Derivative of negative 2t is negative 2, so that's negative 2 times your j vector, and the derivative of 1 is just 0, so that k disappears. All right. So we know that our formula for the derivative of the dot product of two vectors we know that's going to equal dot product of a and b prime plus the dot product of a prime and b. Okay, so if we go ahead and get the dot product of those two, that means we're going to equal the dot product of, and instead of converting those to vector form, I'm just going to leave them as linear combinations just to show how to do this one. So you have a, which is 1 over t times your I vector minus your j vector plus natural log of t times your k vector, and the dot product of b prime of t, which is 2t times your I vector minus 2 times your j vector. Okay, so this is your a of t, b prime of t, plus you have a prime plus b of t. Okay, so you have a prime of t, which is negative 1 over t squared, plus 1 over t times k. And you have the dot product of your b, which is t squared times your I vector minus 2t times your j vector plus your k vector. Okay, so this is plus a prime of t, b of t. Okay, so now to do the dot product as a linear combination. Oh, sorry about that. I will leave you a couple of seconds to write this down. Keep forgetting to look up at the computer screen. So I'll give you a few seconds to write that down. All right. So if we find the dot product of a and b prime, we will end up with 1 over t times 2t plus our j's. We have -1 times -2 plus we have a natural log of t. There is no k here, so that's just plus 0. So you have natural log of t plus 0. Well, times 0. Okay, so plus, you have the dot product of these two, so you have -1 over t squared times t squared plus, there is no j here, so that's 0 times -2 plus, you have the k here, so you have 1 over t times 1. Okay, so we're going to go ahead and simplify these. We have 1 over t times 2t is just 2. We have my negative and a negative, which is positive, so plus 2. And this disappears because that's just 0. Same with this. That's just 0. Okay, so those two just disappear. Okay, so you have negative t squared times, well, 1 over t squared times t squared, which is -1. That's plus -1. And 1 over t times 1 is just 1 over t. So you have plus 1 over t. Okay, so you have 4 minus 1, which is 3. So you have 3 plus 1 over t as your dot product of a and b. All right. Okay, so again, if you are still writing, feel free to press pause. But we're going to go ahead and go to our next section, which will cover the integral of vector valued function. Integration of vector valued functions. Okay, and just like the derivative, it has not changed much since your real valued functions. So let's say if we know that our r of t is equal to f of t times the I vector plus g of t times the j vector. Well, we know that f and g are continuous between a and b. Okay. Then we integrate both sides, of course. The integral from a to b, if it's definite, if it's indefinite, nothing will be there, of your r vector with respect to t is equal to the first term, the integral of the first term with respect to t. You have the integral of f of t with respect to t. Again, from a to b if it's definite, nothing there if it's indefinite. That's times your I unit vector plus the integral from a to b of your g of t with respect to t times your j unit vector. Okay. Or in 3D, your r vector of t is equal to, say, f of t times your I vector plus g of t times your j vector plus h of t times your k vector. Then that means your integral of r of t is equal to the integral of the first term f of t with respect to t times your I vector. Again, that's from a to b, plus the integral of g of t with respect to t times your j vector from a to b, plus the integral of h of t with respect to t times your k vector, again from a to b. Kind of straighten this out a little bit. There we go. Okay, and of course that's with the definite integral from a to b. Okay, so quick note, so you won't be caught off guard. The integral definition is sometimes written down as a capital letter. Okay, so the integral of a function is sometimes denoted as the uppercase of the function. All right. So just for example, so you'll know what to look for in case you forgot. So the integral of f of t with respect to t, they may just call that capital F of t plus c. Okay. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our example of integration. All right, so for example, what if we wanted to evaluate the indefinite integral okay, so the integral of 2t times the I vector plus your j vector plus your k vector with respect to t. Okay, so this is an indefinite integral. All right, so for this one, and I'm just going to rewrite it. 2t times the I vector plus your j vector plus your k vector with respect to t. We just take the integral of each one. Okay, so you have the integral of 2t with respect to t times your I vector plus the integral of 1 with respect to t times your j vector plus the integral of 1 with respect to t times your k vector. All right. So the integral of 2t is t squared times your I vector plus your c, we'll call that c number 1. Okay, so that's now plus integral of 1 is just t, so that's t times your j vector, jumping ahead a little bit, plus our c number 2. plus the integral of 1 is just t, so you have t times your k vector plus your c number 3. Okay, so you end up with t squared times your I vector plus t times your j vector plus t times your k vector plus c. And that's saying that c is equal to c number 1 plus c number 2 plus c number 3. Okay, so as you can see there, not a whole lot has changed between real valued functions and vector functions as far as derivatives and integrals. You just have to be careful for your dot product and cross product. All right, so hopefully this made sense, and I'll see you on the next video.